Oh, now, in time for our panel on chemical mixing. So if you all want to maybe introduce yourselves for a minute or two, tell us a little bit about yourself, what you do, that'd be great.
Who goes first?
Declare you go first.
Okay.
Go.
Okay. Hi, everyone. I am Tim Cunningham. I'm here from the University of Warwick. Primarily, I'm interested in the surface convection zones of white dwarf stars. They're a really fun regime to probe convective physics. I used 3D radiation hydrodynamics with the code COBOL, which was developed by collaborators of mine, Bernd Freitag, Hans-Günter Ludwig, Matthias Stefan. I am interested primarily in convective overshoot, which turns out to be a really important problem for white dwarf surface convection zones, because the overshoot region can be many orders of magnitude more massive than the convective zone itself, by which I mean the distance between the Schwarzschild boundaries. And it's really crucial for quite a few bits of astrophysics which involve white dwarfs. But yeah, that's my primary research focus, so mostly doing numerical modeling with 3D RHD simulations. We use fully compressible hydrodynamics and spend most of the time doing the radius of transfer. But I also use survey data and population statistics methods to probe populations of white dwarfs. And more recently, I've been doing X-ray observations of accreting white dwarfs. But yeah, I think that's enough of an introduction from me. I guess I'll pass over to Sarah.
Great. Hi, everybody. My name is Sarah Martell. I'm at the University of New South Wales in Sydney. And I actually am an observer rather than a simulator. So I do, however, have a lot of the work that I do is very connected to stellar models and to convection simulations, right? So I'm particularly interested in red giant branch stars. I started out looking at carbon depletion and extra mixing and deep mixing, and what models made sense given the data we could get together. And then I'm also very interested in lithium-rich giants and what kind of internal processes might be going on there that would be producing large amounts of lithium kind of spontaneously. So I am also very involved in a couple of very large surveys. So I'm really interested in questions about what data should we be taking and where are the really key places to focus in terms of trying to observationally check on models and iterate with them. I guess I'll pick the next person, Jane.
Thank you. So it's nice that we get a chance to introduce ourselves. I feel like I know so many people at this conference from reading their papers, but haven't had a chance to meet them in person. And I guess I still don't have a chance to meet them in person, but it's still nice to get to hear what people really think. I'm a younger person in this community. I'm in my 5th year as an assistant professor at Georgia State University. My training, my background is in computational plasma physics, where I've focused on MHD. And I got involved with stellar simulations almost a decade ago when I was a postdoc of Isabella Baroff. So I guess that makes me, as somebody said earlier this morning, a 3D person. So I'm excited about plasmas, and in particular stellar plasmas. I continue to be interested in that, even though my main research is working on stars. Over the last few years, I've been working on simulating red giants, and I think those work okay in the simplest setting, and I'm excited about chemical mixing to try to make them more complicated. I've also been working in the last few years on trying to do simulations of binary stars in 3D, and I'm getting more interested presently in trying to simulate rapid rotators. And I guess the fourth in our panel is Amanda.
Thanks, Jane. So I'm Amanda Karakas. I'm also in Australia, though based in Melbourne. I'm a faculty at Monash University, and I've been here about 5 years now. So I'm maybe the most senior of the panel, which is, anyway, it's always a worry when you start to realise you're at that end of the panel. I started off looking, and I still mostly do theoretical modelling, usually 1D modelling of low and intermediate mass stars is what I've mostly focused on. And I started off doing really focusing on the evolved phases, so red giant branch, asymptotic giant branch in particular, and looking at the nucleosynthesis that comes out of these stars. I really moved into looking at heavy element production through the slow neutron capture process in recent years. And now I guess I work on a lot of different things, from chemical evolution modelling of galaxies, also to binary population synthesis calculations with students, so looking at nova production, but also looking at, for example, how binary interactions can affect, for example, yield calculations from, for example, single compared to single stars. So really been looking at a whole lot of different problems in recent years. I guess generally I'm interested in the processes that affect, for example, I guess mostly, let's say, element production in stars, and really mixing is such a crucial aspect of that. So I'm really looking forward to discussing some of these ideas with everyone here. Okay, so what's next?
Yeah, so we've been playing around with the format a little bit, but I think something that's been working pretty well is it sounds like you guys have thought a little about questions you would like to talk about. You're welcome to kind of pick one, go through that. Audience will have opinions. The other thing we've been doing is kind of halfway through, we've been doing kind of breakout groups, letting people kind of chat with their neighbor, get a sense if there are things they want to hear about or questions they'd like to ask, and kind of kicking it back and forth. So we'll probably do that for about 10 minutes, about halfway through, if that's all right with you all. If there's a question you guys would like to start with, that might be good, and just let the discussion wander. Also, I know you have a slide. Would you like that shown? And if so, could one of you share it? Otherwise, you can just kind of talk from it. That's fine too.
Yeah, I guess it's a bit awkward to share a slide with and be able to see everyone. So we can maybe save the slide until the breakout.
Yeah, that sounds
session,
great.
And then we can have those as a focus for that.
All right, so where would you like to start? Observations,
yeah.
wish list, desires, complaints?
Actually, I think, so since Corinne talked about thermohaline mixing this morning and rotation, maybe this is a nice way to connect what Corinne talked about with, I think, I mean, quite a few of the questions that I think that, well, that I'm interested in, and hopefully I think Sarah and the other panel members are these questions about thermohaline mixing and rotation. And I guess one thing I would like to talk to about, and hopefully if I see that Corinne's still with us, is this question of, thermohaline mixing, we know happens in red giant branch envelopes. It leads to mixing. It seems to happen. We know there's still issues with the formalism as used in 1D calculations. Is there where to from here? Because we know that there are, we can't, it's really troubling. We still have trouble getting, say, carbon and lithium right. We know that there are some issues. How can we improve what we have to move forward? Maybe this is something both from an observational point of view and from maybe hydro modelling point of view. I'll leave that out there.
Well, I love this question because I think that there's a lot of space to experiment. Yeah, right. I know that the Korean and Nadej have very well developed code and approaches for looking at how surface abundances change as a result of rotation and thermohaline mixing and other processes. But there's still a lot of questions around what if you change the mass to this, or what if you Kate Henkel, who was a PhD student at Monash a few years ago, turned the metallicity all the way down just to see what would happen, and how that would change the way that you need to parameterize the mixing in order for the model to work. And I just think that there's so much space for trying things. I think that's also the downside, right? Is it's hard to know what the right way to go is. I think one of the things that I took from Kate Henkel's work was that a single diffusion coefficient is not the most informative way to think about extra mixing, which could be lots of things. But I'm not sure what the right way is.
Can I? Yeah, you're talking about the work of Kate and the observations in globular clusters.
That's right.
Is that correct? So as far as the carbon isotopic ratio is concerned, I think we get pretty right, both from the observations and from the models. Carbon and nitrogen is a little bit, carbon over nitrogen is a little bit complicated because in stars of masses around, let's say 1.8 to at solar metallicity, you also have some nitrogen enrichment from rotation on top of thermohaline mixing. So rotation on the main sequence that leads to a slight increase in addition to the variation on the red giant branch. And I don't remember if in her models, in Kate's models, that was the case. And from the observation, you should tell us if I think it's easier to get the isotopic ratio right than the carbon to nitrogen. No? Is that correct? Or?
They require very different data. So it's just a matter of what's been done, basically.
And the other point is that I think in globular we should have a look at what happens if the stars have slightly different initial helium abundances, because that might change a little bit the structure of the star. And it's something that I wanted to do for quite some time, actually, to see if when you do that, if you really need to change the diffusion coefficient or not, as Kate was finding. It would be quite easy, actually, to try to do.
I think that
the question of lithium. Sorry, Sarah, but lithium is still problematic. If you can match carbon, you still have the issue of lithium. And I think that it maybe points to a deeper problem with how we treat thermohaline mixing, because they are burnt at different temperatures. So it seems that if you match carbon 12, carbon 13, lithium is destroyed completely, so compared to observation.
Yes.
So
that's what we see at the bump. If you look at the globular cluster
exactly.
at the bump, the observations of Karin, for example, and some of you also, of Sarah, etc., you see lithium is totally destroyed above the bump, no?
Yeah, but the models are, anyway, the models, maybe this is an issue. I think the models don't match that aspect very well. The models destroy it far more than is seen from observations.
Far more lithium?
Yeah, it destroys far more lithium than is seen from observations.
Sure, but you see no more lithium above the bump. I don't know, Sarah. Depending on the mass, of course, and on the metallicity, because if you have a star of 2 solar masses, you don't expect much lithium depletion.
Right. This is, I guess, one of the things that I was thinking about. So Daniel sent us all these questions about, what are the questions right now and what are the challenges. And one of the things that makes it difficult to get an observational data set that's useful here is that there are not a lot of 2 solar mass red giant branch stars around. And and this, I think, will this gets better with time, right? As Sloan continues, as Weave and Foremost get started. Although these stars are rare, if they're rare in a larger sample, then we will have more of them that we can use, which I think will be really useful.
But
Actually,
how many of these stars you have in Gala samples, for example?
Massive giant branch stars. Well, two solar mass giants. Not a lot.
Not at all.
This is Jamie Tyre. I'm just going to jump in so that we can get some discussion going. Just because we've been thinking about this here actually at the program with kind of the Apogee Kepler sample and the Sloan sample and the Gloss. Like there are actually quite a few stars where we can trace lithium, C to N, C12, C13. So I think that's actually a really interesting way of going about things. And I think that data is here or approximately here. So that's really cool. Other questions?
This is Adrian Fraser. So I do work on the simulation side, 3D, MHD, thermohelium mixing, and I hear the three of you talking about there's still questions. The three of you are talking about there's still not much understood about thermohelium mixing, and I'm curious. I mean, you're clearly coming from a very different perspective than I am, and from my standpoint, depending on what you tell me the magnetic field strength is at the base of the convection zone in RGB star, it's gonna, from my simulation, I think it has a huge influence, and from Peter Harrington's simulations, I mean, it'll have a huge influence on the efficiency of thermohelium mixing. So, I mean, yeah, I think any model that's, there's a bunch of huge open questions on the simulation side of how efficient thermohelium mixing is. And so I think I'm still new to this, so I don't know what work has been done on your all side of this, but I'm guessing that there's still giant error bars in the efficiency of thermohelium mixing as implemented in most stellar evolution codes. And I guess whatever direction forward it's taken, don't you think it'll still need a lot of work on that?
The only parameter I would say is the aspect ratio of the fingers.
Well, that's something that I wonder about, Corinne, is that if we have some people who are doing these rotating three-dimensional magnetic models, and then we're trying to, represent all of that as a diffusion coefficient. I mean, I understand computationally why we do this, but I do kind of wonder if that's the best way to represent to sort of bring the dimensionality down. And maybe Adrian could say more about that.
I think should be the 3D.
I'm not Adrian, but I'm Daniel Quanet. I think of course, the nice thing about a diffusion coefficient is that it's the easiest way that you can describe things. I mean, even in Corinne's talk, she mentioned how you can have advection, which, I mean, it just has a different form than a diffusion coefficient. But yeah, I think it's an open question of kind of like what are actually the best ways to describe these things. And at this stage, unfortunately, I would say diffusion coefficient is kind of the best that we can do. I know Tim has been looking at diffusion, kind of trying to figure out how to do a 1D description of what you're seeing in 3D simulations, although in a different context than thermohelium mixing. Maybe you could describe some of your efforts on that.
Yeah, absolutely. So yeah, I'm primarily studying white dwarf surface convection zones, and as Daniel says, trying to extract a 1D prescription for the diffusion coefficient due to overshoot mixing in that regime. Some of the challenges, well, some of the successes we've had there is deriving the first diffusion coefficients for convective overshoot in degenerate stars. And it has a really big impact on studies of metal-polluted white dwarfs primarily. And there's a couple of things I might bring up about that. So some of the challenges I'm facing are that the physics of overshoot is changing quite rapidly as a function of white dwarf cooling age. So I currently have studied white dwarfs from 100 to 500 megayears after the formation of the white dwarf. But there's a marked change towards the larger cooling ages and the morphology of that overshoot region. That's kind of the main reason that I came here, was to try and see if we can understand something deeper about the physics of overshoot in this grid that I have, and see whether we can connect with overshoot models for core convection, which we've heard a lot about today. But thermohaline mixing also has a really big impact potentially for these accreting white dwarfs as well. So Evan Bauer had a paper a couple of years ago which looked at thermohaline mixing in 1D. So a response to Adrian from my side is that I'd really like to see some hydrodynamic, multidimensional hydrodynamic simulations of thermohaline mixing to probe whether the steady state can exist. So if you accrete metals and you keep replenishing from the top some heavy elements at the top of your white dwarf, what effect that has on the instability? Does it cause the instability to grow further? Or yeah, so I'd be interested to hear your response or to motivate some work there.
Hi Tim, it's Dominic here. You said something in your intro that's really intrigued me. You said that in some of these white dwarfs you have more mass in the overshooting region than in the core. Is that correct? Did you say that?
That is.
How did you say that?
Yes, correct. Yeah.
Okay, can you explain a little bit what that means? Like from our talk this morning from Anne, what do you mean the mechanical? Oh, Evan as well, actually, the mechanical overshoot. What are you putting in that term overshoot?
So so this is where our dictionary of convection regions is going to be really important, I think, to by the end of this program at least. But the way I've modeled these convection zones is to take the Schwarzschild boundaries as a measure of the convection zones, of where the instabilities can grow and where eddies are formed. And for me, the overshoot region is any region outside of that with hydrodynamic flows. So primarily overshoot plumes that are penetrating into the stable layers, the stable radiative layers underneath. And for, my grid was designed to probe the onset of convection in white dwarfs. So as the white dwarf cools towards where the hydrogen opacity is a maximum, so that's around 12,000 Kelvin. When you get to about 18,000 Kelvin, the hydrogen becomes partially ionized, and that's what allows a superficial convection zone to grow. And it really starts from nothing. So you can have a convection zone that's like tens of meters, and that will eventually grow. And by the time the white dwarf is a few giga-years old, it will eventually couple with a degenerate core. But I'm probing this regime where it's actually rather superficial convection. So we start with Peclet numbers of 10 to the minus 6. And 10 to the minus 6. And we, by the time you get to a white dwarf of about 500 megayears, the Peclet numbers reached sort of order unity. And so we're in a very extreme regime as far as convection goes. It's a very different picture to the core convection that we've been seeing. And I think that the large radiative temperature gradient beneath the convection zone is what allows you to have this really large overshoot region. But it has, there's two big implications. One is that it directly impacts how much accreted metals, well, your inference of how your accreted metals. So it has big impact on evolved planetary system science, which I can say more about at some point. But we also have managed to provide a constraint on late thermal pulses during the asymptotic giant branch. So these simulations have allowed us to derive a mass distribution of thin hydrogen shells in white dwarfs, which provides some constraints on the hydrogen content.
So maybe I jump in here and talk more about simulations. So one of the things that's really interesting about this whole topic of chemical mixing is that it's basically an extreme challenge for computation. When you want to simulate how chemicals interact, you have to be simulating on incredibly tiny scales, both spatial scales and time scales. And if you want to simulate how a star actually works, you also need to be simulating on enormous scales, I mean, literally astronomical scales. And the difficulty with this is that a computational grid, can't cope with both of those things simultaneously. And so one of the big challenges for improving models in this area is just figuring out a model that you can use to do the computations. When you're doing a simulation of the whole star, then you have to have a model for how the chemistry or the thermohaline mixing changes things below the scale of your grid at the smallest scales, how that injects energy or interacts with turbulence or any other thing that's very small. In this way, this whole question of chemical mixing is as challenging as magnetic fields, just because those very small scale effects will change the large scales, or at least the larger scales of the flow. So this is something that I think is fascinating. What we can do in this whole field of simulation, we can do direct numerical simulations, and I think we've heard from people who are doing those, which are doing a rather fundamental simulation of how the chemistry gradient changes small scale convection. And that's very informative, but doesn't tell us how the whole star reacts. As we know, one of the really basic things about convection in stars is that it's a non-local phenomenon. So if you change some small thing at the boundary of a convection zone, that changes the character of the convection all the way through the convection zone. It changes the scales of the convection that are produced and how those scales interact. So this is sort of throwing this out there. This is a challenge that I think about and a challenge for the community. How do we incorporate our ideas about thermohaline mixing on a fundamental sense into a more realistic full star? I think this is a step forward that we could then try to crunch down and make a diffusion coefficient that would be more detailed, maybe more accurate for 1D stellar evolution.
This is Adrian Fraser again. I really appreciate what you said about direct numerical simulations and the role they play here. I think there's still a lot of open questions about the efficiency of thermohaline mixing on a fundamental level when you do these direct numerical simulations. I kind of wanted to go back also to what was said earlier in context of white dwarfs. I mean, there's really, really good models in the hydro case. If you know the temperature gradient and the mean molecular weight gradient, then without needing to ask about the aspect ratio of the plumes or anything, you know, that Brown et al. I mean, there's a lot of good work that came out of Pascal's group in the last 10 years, getting you a model that you could use there. I guess I wonder, does that not get you what you need in the context of white dwarfs? I wasn't quite sure what the setup of the problem statement was there. It sounds like maybe you're talking about a fixed flux problem as opposed to a fixed gradient problem.
Yeah, well, my wondering was, yeah, once you trigger the instability, then you affect your mean molecular weight gradient, right? So Yeah, I guess I'm not really familiar enough with thermohaline to know then once you've triggered the instability, once you keep adding metals, whether that forces the instability to keep growing. But I don't know enough really to know if that question even makes sense, but thank you.
Yeah, for Karvik, I want to, first of all, Jane, I really can only second your expression of frustration, how hard it is to measure these small mixing effects outside the convection zone. And I can maybe really briefly share an experience that we had over the last year where we tried to measure in our 25 solar mass stars the mixing due to internal gravity waves by placing a dye essentially right into the simulation with very high resolution. And and initially we saw some mixing there at these very small levels, but although we were using Paul Woodward's high order PPB advection scheme and doing it on a 2,688 cube grid ultimately, and we have lots of waves in there, and it's very active, but we were ultimately not able to measure, we were able to measure mixing coefficients, but we were not able to convince ourselves that we had converged results. So I can only, second this point that it is very hard to measure these small secular timescale effects in 3D hydro. With regard to thermohaline mixing, we had a discussion in the program one afternoon, and I thought I learned that despite the fact that we had about 10 years ago hydrodynamic simulations that showed by Pascal Garot and by Pavel Denisenkov and his collaborator that showed that the aspect ratio in stars in stellar conditions would be very small, and that sort of I thought had sort of killed that whole field of thermohaline mixing. But I learned here that it is possible to maintain thermohaline mixing in the face of magnetic fields. And so to me, it seems that the most important thing with regard to thermohaline mixing would be to see whether the presence of a magnetic field is reasonable, whether it can be observed, what kind of other implications it would have. And that seems to me the most important thing with regard to thermohaline mixing at this point. Because otherwise, without the magnetic fields, it seems it's dead.
Not to derail the discussion on magnetic fields, but I just want to mention that there's been some interesting discussion in the chat. I want to loop everyone in on that so that everyone else can participate in that as well. Start with some question from Pascal Garot about whether or not there's a problem of lithium versus carbon in the observations. Can the same diffusion coefficient explain both lithium and carbon abundances in RGBs or not? It seems like Amanda thinks that the answer is yes, there is a problem that you cannot use the same diffusion coefficient, which would be a problem for normal hydrodynamic models where all the chemical species would be diffused in the same way. Although my understanding reading this is that there's the data is maybe not so clear. So maybe you can expand upon that a bit further, and we can continue discussing that here as well. Go for it, Corinne.
Yes, I had the paper of Kate under the eye actually, and so the lithium it's mostly upper limits, so I don't think it's really a problem. You want me to share the slide, or it's not a slide actually? Can I share?
Sure, I think it'd be worth showing. I think it needs checking with other cluster data. That would
You
be,
see?
I think, yeah. Thanks, Corinne.
Okay, so the data are the ones of Lint, I think, for lithium. So it's for MGC, I don't remember which one, 6397 probably. So here you have upper limits.
Oh, there's three
And-
data points. So there's 3 data points and 4 upper limits.
These two ones, yes.
No, also there's a third as well. That's not an upper limit. So there's 3 data points and 4 upper limits. So it's, I'd say, marginal, whether it's.
But here you have the error bar on carbon, which is quite large. So I guess I think we would have the answer if we would have carbon isotopic ratio. So what we need is carbon isotopic ratio in these stuff.
All right, Jamie, I think we have our work cut out for us.
Agreed.
We have our assignments. Yeah, so we always go back to this Lind paper in 2009 to talk about lithium and extra mixing, because it's literally the only like decent sized data set in a globular cluster. And it's just been a difficult thing to gather observationally. It's a great example of how this behaves in clusters, and it is clear that the abundance does not completely go away, right? When the above the RGB bump, the abundance does not go like completely to zero. It still trends downward in that exponential way that we would expect. And so we can do something about the diffusion coefficient with that. You know, we can say that it can't be larger than some value. But to really understand it better, yeah, we would need to get more metallicities, and higher mass stars would be nice, right? There's a lot of stuff that is just challenging to get together observationally.
I wanted to show you the data, actually, if I can find it again. Where is it?
This might be a good time to kind of pause and see, kind of have little group discussions and see if there are questions people want to talk about.
Okay.
So if you all have, maybe, do you want to put up your slide? And if there are a couple of questions you want people to focus on or discuss that you want to kind of cover in the second half of this, that might be great.
I've got the slide, so I can share that.
That would be great. Thank you.
So let me just.
We have a colorful option and a less colorful option.
Colorful option.
Yeah, that's what
Colorful option. There you go.
There you go. Nice.
Right. Do you want to pick maybe a couple of things that you want to focus on?
I guess I already started us off with. So is this for breakout rooms, Jamie?
Yeah, exactly. We're gonna break out into small groups, 6-ish people, get a sense of kind of what's happening in the room, what people are interested in, talk for maybe 10 minutes, and then kind of come back and hear kind of what each group was discussing, what they were interested in, let you guys react to that, and kind of continue the discussion that way.
I would say any of the questions.
All right.
Yeah, I mean the top ones are the ones that we've thought about, and then the bottom ones Daniel will recognize as the ones that he told us.
Just zoom in on the
about.
top ones.
So yeah, maybe let's go for any of those top ones.
They're a little small.
They are a bit small, yeah.
Okay, don't know how to make it bigger.
Get rid of the sidebar, maybe.
Yeah. They would like to know what the colors mean.
I think they're different. Actually, that's a good question.
I think that's by author. Yeah, by panelist. There's no specific meaning of each color. But mostly it was a way to make a million questions look interesting. Is it too small?
A little too small? How's that?
Yeah, why don't you read them out, and then we'll kind of collect into groups for 10 minutes, okay?
Okay, so question 1, we have, how does chemical mixing and the stratification of chemical layers in the RGB change the character of MHD? I think that's the end of that sentence. And then we have number 2, how does that change between RGB and the AGB? Shall I keep going? Is this
Sure.
effective? Yeah. Okay. Number 3 is more generally, what drives non-convective mixing in RGB and AGB envelopes? 4, a more specific related topic. A small fraction of HGB stars also show surface abundances consistent with non-convective extra mixing mechanisms, I guess, is unlikely to be thermohaline mixing in HGB stars. So what is it? Magnetic fields, question mark. 5, what are the physical properties that describe the extent, basically overshoot? That was one of my questions. Can we do better than an exponential F overshoot formalism? I think the answer is yes, but yeah. 6, how do magnetic fields affect convective mixing? 7, how can we compare the nature of overshoot for core and surface convection zones? 8,
Sorry, let me start again.
I can't remember it. Starts with is. Is there a tech revolution coming for rotating MHD simulations? Do quantum computing or neural networks offer any possibilities? And 9, what are the aspects of mixing that we are most confident in our understanding of, that observers should focus on gathering comparison data for? So we'd like a good answer for all of those questions, please.
Groups. It sounds like we've had some interesting discussion. How about we hear from some of the groups, what they talked about, what they'd like to hear more about? We're going to start here in the back of the room. Somebody want to report?
So Evan Anders, we kind of broke off into a lot of different conversations because we are a very cohesive group. I'll say what Lydia and I were talking about. So Lydia did a cool paper in 2019 and found that the overshoot in her simulations, this is like the dynamical mechanical overshoot I was talking about, falls off the kinetic energy falls off like a Gaussian instead of like an exponential. So that could be an interesting thing for us to look at as far as like F overshoot models. Anybody else here want to say what they were chatting on or have any?
This is Mathieu. We also discussed like all the kind of instabilities that there can be in a stably stratified region. And well, personally, I care a lot about core overshooting for black hole masses in massive stars.
All right, how about over here? Anyone want to report?
I think the main takeaway from our group was that, this is Adrian Fraser. The main takeaway from our group was that we still don't have models for the efficiency of thermohaline mixing, at least in MHD, that are consistent with simulations at Prandtl numbers of 10 to the minus 2. And we need to get that down before we can extrapolate them to 10 to the minus 6 and really trust them in stellar models. Is that fair? Yeah.
All right, what about this group? Would you all talk about?
Okay, so Rafa Garcia. First of all, we were not expert at all on any of this. So we moved to what we mostly understand better, or not understanding, machine learning and the application of machine learning, one of the questions that were there. And we all agree in the panel that machine learning is very useful for classifying, interpolating, clustering, etc. But to use machine learning to something that we do not understand very well and then try to understand physics from what the machine learning is really telling us, we were not probably going to do this step, at least in the panel. So then we're moving to what seismology could help on convection. So we're saying that for that we need to prove the external part of the star. So we need to move to the stellar imager or any imager that we could do. but that there are technical problems there, etc. But yeah, it's worth trying maybe for the next generation of satellites and for the young people to push for it. And I don't know, something else. Yeah, well, that's probably.
All right. How about over here?
Hello, Australian fam. How are you doing? This is Meredith. So I have an extremely, Amanda's laughing, that's good. An Amanda-specific question, which is like in the context of chemical mixing and all of these things, what is the third dredge up sensitive to? And then I also have like a broader question of do models over or under predict lithium abundances, and where, and is there even a consensus on that? And then I don't know if either of you have something to add.
So this is Dominic. I'm not a low mass person. I'm a heavy person. What I don't understand, I'd like to gain some insight on this, because we've been talking about this amongst the wider program, but maybe it's good to mention it here at the conference itself, are we data limited in this problem of thermohelium mixing and lithium abundances? Like, what's the perfect set of observations that you would want? Because I don't have a very good grasp of that. Is that lithium abundances in clusters? So if someone can give me some hints on that, that would be very helpful. Thank you.
Well, I've got a wish list if you want to hear it.
Go.
All right. So yeah, lithium abundances, but in astroseismic fields, so that we have masses. Corinne in chat says carbon isotope ratios, and she's absolutely right. That's most of it. The thing that really would be useful is the thing that's the hardest to get, which is a range of mass, a range of metallicity. So if we're only looking at clusters, we're only getting low mass stars, and generally we're only getting metal poor stars. And we know there's some iffiness in seismology when you start turning the metallicity up and down. So the whole thing needs to be sort of co-calibrated to work in that whole parameter space.
We have one more group over here. So what did you all talk about?
Hi, this is Philip. We talked about NDF overshooting parameter, or just overshooting in general, and how it affects the wave excitation, in particular what it does with the subsurface convection zone, how that affects the wave excitation, because we don't talk about that much. And what else? It was appreciated that the RGB and AGB were mentioned, because so far this has mostly been a main sequence conference. So you can talk more about that and make some people happy. Anything else? Oh, you have to say it.
All right, we can touch it here. So I'm also interested, or whatever, are interested in atomic diffusion in chemically peculiar A-type stars, where we know that this is ongoing, and how this affects the excitation of pulsations, because we know it does.
All right, are there any of those things you want to, oh, did I skip one? Oh, the Zoom people, of course. Go ahead, Daniel.
I'm not a Zoom person, but maybe someone on Zoom, or maybe one of our panelists, can describe what you were discussing in the Zoom breakout room.
Yeah, we mostly discussed, if it's okay, I'll mention what we talked about. We mostly talked about that there's a small fraction of HGB stars that seem to show extra mixing, and whereas some stars of the same mass and metallicity do not show any. In fact, they show the opposite behavior. These are carbon-rich stars compared to oxygen-rich stars and clusters. I wondered I don't know if it's thermohelium mixing that drives it. People have looked into this question in the past, but maybe it's a mass issue, as Corinne mentioned. Maybe these stars might be massive enough to show thermohelium mixing on the early HGB, but it seems it's happening on the thermally pulsing phase. And any ideas of what could be driving this extra mixing in thermally pulsing asymptotic giant branch stars? We didn't have an answer.
Daniel Quine, a follow-up question for that. When you have stars that are in similar phases of evolution, solar mass, etc., but then you see these different chemical abundances, what's different about them? I mean, is it rotation rate? I mean, that's something that maybe could be measured. Magnetic fields. I mean, are there any observational probes that can distinguish between these?
Is that a question to me or to the
yes.
to my comment? Well, these are HGB stars, so you don't see much stellar rotation. They're too big and puffy for that. So their cores might be, but you don't see any on the surfaces. And so the comparison is usually stars in a cluster, and you have a sample of oxygen-rich stars. So these haven't experienced thermal pulses yet, and they have a certain C12, C13 ratio. And then there's carbon-rich stars. They're on the thermally pulsing phase, and they have essentially the same C12, C13, but they should be higher because you're dredging carbon from the helium shell, so carbon 12 should go up, but it hasn't gone up. So I don't know if rotation could be, but there's no evidence for rotation of the stellar surfaces. Magnetic fields, don't know. It's hard to, I'm not sure. I'll just say that as a I don't know question, maybe. Thermohelium mixing, maybe. If there's still helium-3 left if they haven't experienced thermohelium mixing on the red giant branch, they might have on the HGB.
Well, so Amanda, you said something at the beginning of our Zoom breakout conversation there. That the thermohelium mixing specifically has to do with helium-3. And it's actually, I mean, any kind of double diffusive instability, I guess I'm thinking of them all as kind of the same thing. Or semi-convection or something that wouldn't necessarily need to be specifically the helium-3 thing, just that you've got the cool dense part and the hot low density part. Maybe I'm grouping too many things together.
Yeah, you have to have something left. Yeah, I mean, helium-3 works because it's left over from PP chain from hydrogen burning on the main sequence, but I'd have to think about that. I don't know, Sarah. That's a good question.
Helium-3 works because you produce more particles in the helium-3, more particles at the end than at the beginning. So is there any nuclear reaction that could do the same thing in HGB star?
So this is heavy Dominic again. So I'm aware of some recent results on HGB stars and post-HGB stars that turn out to be binaries. How does this relate to like chemically peculiar stars on the tip of the HGB, so to speak? Are maybe all these stars binaries? Question mark?
Binary, working out of an HGB stars a binary is really hard because, again, the big and fluffy. Maybe, but it just seems that only the carbon-rich stars then are binaries, and then all the oxygen-rich. Anyway, I don't know. Maybe it seems a bit. Maybe.
Are you thinking about pollution, or are you thinking about tidal effects that could induce some mixing?
Yes, basically pollution. So I'm aware of a few results, particular PhD student Shreya Shetty, who's now in Geneva, I believe. And the transition from mixed to polluted stars, I think, is related to that, if I'm not butchering her PhD thesis in that one sentence.
But I wonder if it works for HGB stars. I mean, you need to have a very thin convective envelope for the accreted material to change the abundances. It works on the main sequence because you have a very thin convective envelope. So you have if you have a main sequence star which is accreting from an HGB, then you can change the abundances of the main sequence star. But if you have two HGB, the convective envelope is so large that you really need to diverse the amount of mass of the convective envelope, which is about 80% of the mass of the star.
Yeah, I was going to say that in sort of a less technical way, but when you think about mass transfer in an HGB binary system, it's usually from the HGB star.
Yes.
Onto it.
Although I think I know the work you're talking about, the paper from, I think I read the paper from that you're mentioning. I don't think that would be the solution for this particular problem. I think these are stars that were binaries. They accreted matter, then they became HGB stars later in their own evolution. So yeah, maybe I don't know if binaries are going to help us here. Other problems, maybe.
I'd love to know what Corinne was saying about tidal interactions inducing some kind of internal motions. I'd love to know if this group thinks that's a reasonable thing that might happen.
Hi, Vicky Antochi here. It's not related to binaries, my question, but to pulsations. As far as I know, and that's really from the very back of my brain, HGB stars do pulsate with pretty large amplitudes. So I wonder, to what extent do these pulsations mix or do the interior of the stars?
Yeah, so HGB stars, they do show these large scale, large amplitude, these large amplitude pulsations. They tend to be mostly radial pulsations. They certainly change. I mean, the radius and luminosity will change over a pulsation period. I don't know if this is pulsation driven. It's in the envelope. I don't know if this is going to drive, and the envelope's already fairly well mixed. It is well mixed, I suppose, and I don't know if this radial pulsations will lead to further mixing between burning shells. I don't think this is not modelled though. The 1D stellar evolution calculations don't generally they don't include radial pulsation modelling at the same time, and then the timescales are too different. That's what I'll comment on that. But I can see Meredith's hands up, so she may say more.
Well, yeah, so if you want to look at a situation where you can analyze the actual thermal pulses and the astroseismic definition of pulsation simultaneously, then Molnar et al. 2019 is a really good place to do that. So go look at that. Also, I'm on it, obviously.
I got a mic. Yeah, just to pick up on Vicky's question about pulsational mixing. For white dwarfs, like sufficiently cool, actually right around where the hydrogen opacity is greatest, you can drive G-mode pulsations, the ZZ SETIs. So I'm interested if anyone's got any thoughts on, it's thought that there is, we know there's convective overshoot happening there. It's also predicted in Evan's paper that, Evan Bauer, that is, that there should be some thermohaline mixing underneath that convection zone. I wondered if anyone had any thoughts on the properties of that thermohaline mixing, given that there are G-mode pulsations being driven by the convection zone. Because I have no idea. Okay, great. I see a hand.
I feel like a jerk taking the mic so much that everyone's looking at me. So you're saying, this is Adrian Fraser, said jerk. You're saying if you have thermohaline mixing, unstable region below a convection zone, and we know, thanks to Evan's great talk today, that you have convective penetration happening, what does the sum of those two things do? Is that the question?
No, I'm more interested in, at around 12,000 Kelvin, white dwarfs will pulsate with G-mode pulsations, which is driven by the convection zone. And so those G-modes are propagating in the region where it's predicted that thermohaline mixing instabilities can live. So I'm wondering what the interplay between G-mode pulsations and thermohaline mixing would be.
So you're like what? So okay, sorry, I'm translating because I don't know much about stars. Is it like asking what happens if a gravity wave comes through a thermohaline mixing region?
Yes.
Cool. I don't know. Sorry.
Great. Good.
Let's work on it.
Yeah.
But at least you assume that there is a thermohaline which is already a progress.
Sorry for hitting the mic on my chair. This is Evan Anders. I also don't know exactly what happens when a G mode goes through a thermohaline region, but I do know that like in simulations, just because a region is unstably stratified doesn't mean you're going to get the instability. You have to kick off the instability somehow. So it's possible that these G modes could be something that kicks off thermohaline mixing. I don't know, but that would be the main thing I mean, it's probably happening already anyways, but like, if it's already happening, can you still have waves going through it? Is that what I asked you yesterday in your talk and I'm asking you again? I'm sorry. I'm the worst.
You're asking, can a thermohaline mixing unstable region support gravity waves traveling through it that are excited elsewhere? While it's already thermohalining, is what he said. I don't see why not. I'm looking at Daniel because he knows more about waves than I do, but you still have a Brunt Basala frequency there, right? I mean,
my question for you is, this is Daniel Quine, is n squared positive? Then yes, there are waves.
Yeah, right. So I like maybe I alluded briefly in a talk, despite some controversy, that there's, whether or not there's waves generated in thermohaline mixing regions is a question. And so if they are, then like who knows what they do interacting with other internal gravity waves that go through them. But yeah, it should work. Yep. Evan gave me the thumbs up. I'm going to let go of the mic.
This is Daniel LeQuine again. I want to ask Jane a question. This is kind of reaching back maybe in an hour or so. That Tim mentioned that there are these prescriptions of convective overshoot, extra mixing due to convective overshoot, and those are often numerically calibrated, or maybe it's something that you kind of fit to data from observations. But I know that you've been working on kind of some theoretical motivation behind various profiles with extreme events and stuff like that. I thought it would be great to hear from you about some more physical models of overshoot.
Yeah, sure. I can say a few words about that. So this was a postdoctoral project that I worked on at the University of Exeter with Isabella Broff and the developers of the music code. The idea was to do 2D and 3D simulations and that would be sort of global simulations of the star, and to measure the amount of overshooting and to use those detailed measurements to construct new stellar evolution theories. There were some insights that we gleaned from these simulations. One of these insights, maybe not so much from the simulation, but we saw this also in the data backing it up, is just this idea that convection is a very intermittent process. So you see convection rolls or plumes that gain a lot of energy, and you see those things fairly frequently, but they're not the majority of the convection rolls or plumes that you see forming in a convection zone. When we see these more energetic plumes crossing the boundary of so the convective boundary, this boundary of instability, they seem to have an outsized effect on the region below the convective boundary. So we were looking at convective envelopes in this case. This outside effect, they were exciting internal gravity waves that had a lot of energy in them. So that, I think that's all not very surprising, that a plume that has a lot of energy will pass on more energy to an internal gravity wave. They were also penetrating more deeply. So I looked at the statistics of where plumes were penetrating, and also possibly not surprising, although something that we hadn't thought about before this study, was that this is not anything like a Gaussian distribution. And it's not surprising that it's not anything like a Gaussian distribution, because convective plumes don't stop before the boundary, so that there's a cutoff on one side of this distribution. So this is something that can never be modeled with a Gaussian distribution in a satisfactory way. Beyond that, when you resolve these simulations really well, you find that these more energetic plumes form a heavy tail on the distribution, or a heavy wing, and that where that wing is placed is actually defining where the most energetic of these internal gravity waves are being excited. So the theory there that I came up with was to use the maximum amount of penetration at any point in time to measure the width of this layer that's really being churned up all the time. At any point in time, there are 2 or 3 of these energetic plumes that are getting across this convective boundary. This is using the maximum is something that defines this layer so much better than the average. If you take the average, which is what people had been doing, then that average line sort of hits at an awkward place. It doesn't hit at the place where the energetic plumes are getting to, but it also doesn't hit at the place where all the kind of weak plumes are getting to. So it's sort of in the middle, and not targeting any of the physics of this overshooting layer. So this is the insight that the average of these plumes is not really useful, and the maximum is. That allows us to use a branch of mathematics called extreme value theory to put a form on how this diffusion coefficient should taper off. And that form is a little bit different from this exponential decay. It's something that's a difference that you might not have noticed if the simulation wasn't really very well resolved. But there's a little bit more in the area where plumes are sort of weakly penetrating, and there's a little bit less in the lower regions, and so it's got a little bit different curvature than this exponential decay. It ends up being an exponential of an exponential decay. So this is what I propose, we propose, as a somewhat better diffusion coefficient to use, particularly under a convective envelope. I think this insight is not specific to the kind of convection zone, and there's a good chance that such an idea would work also for convective cores, or convection above an envelope, so convective overshooting above an envelope. Those are things that might be calibrated differently. So that's the idea for this overshooting coefficient, and it's not going to change anything profound. It's just a little bit better, and that allows you to get closer to observations in the end. Isabella then tested this out on the lithium depletion problem and could show that it does indeed get closer to measured values of lithium in the sun. So, I hope that's a good amount of detail to have gone into.
Thank you. In the last few minutes, I'd love to have kind of each of you take about 2 minutes and summarize kind of your takeaways from the panel, or things you thought, you want to highlight again, or things you wish you had had time to talk about but we didn't get to. So kind of 2 minutes. I guess, Jane, would you like to go first?
So takeaways from the panel. I think, so there was a lot of discussion about what the observational data tells us what data is there. That's really interesting, but for me as a person working with simulations, I would like a short review of those things. So the details are hard to keep up with. What was the idea that's important for me here is that I think we all need to sort of work together. We should have a grand challenge program for simulating and modeling and measuring everything about red giants and HGB stars so that we can actually make progress on this problem. And as far as simulations, I think what's notable to me is that so a couple of years ago, there was a stellar hydro days at the University of Exeter. And Falk mentioned at the end of that conference that nobody that was present there was simulating HGB stars. And I think that's still true. This is something that particularly for people who are doing simulations is definitely a grand challenge problem to produce more simulations of HGB stars.
Great, thanks. Amanda, would you like to go next?
Yeah, sure. I guess I really enjoyed the panel discussions. I think I've really enjoyed first hearing Corinne's talk this morning and hearing more about thermohaline mixing, and then the discussions we've had about that issue. I think one thing that would be, it seems, I think, one way forward, and this is really putting the problem back to you and to Sarah, we need more data. We really need, I think, in order to, I think if for this problem, I think first of all, in order to see if, well, I think first of all, we need carbon-12, carbon-13 and lithium and carbon and nitrogen in clusters, possibly clusters. I mean, because at least then we know something, these are hopefully all homogeneous, they have the same metalist, etc. So I think thermohaline mixing, maybe for the, in the immediate step, hopefully we can make some, move forward with better observations. One thing that, so we also discussed, at least in the breakout room, we discussed whether this small fraction of HGB stars that may experience extra mixing. I think this is something, first of all, when it happens, is it an early HGB extra mixing driven by thermohaline mixing in those stars that didn't have it on the red giant branch? Does it happen on the thermally pulsing phase? If so, what is driving it? One thing we didn't discuss, and this is a question that Meredith raised, and it was something that I was really quite keen on discussing, obviously don't have time, is about the dredge up, which is this mixing that happens following a thermal helium shell flash. We know it happens. We see S-process rich stars, carbon rich stars, but it seems there's some stochasticity to it. That's probably, I can't probably pronounce the word. Because there are stars of 1.82 solar mass that should be S-process carbon rich but aren't. And then there are low mass stars. This is especially work coming out from Sophie Van Eck's group, some of the students and postdocs working with her, that have found really low luminosity, slightly carbon rich, S-process rich stars. So it seems it happens at lower mass sometimes than we expect, and then it doesn't happen in higher mass stars when we think it should. So I think that anyway, that needs more discussion. And more hydro models of HGB stars, please, Jane.
How about Sarah? Why don't you go next.
All right. Well, I think the main thing I've gotten is that we have some homework to do in terms of the data set, which is great. I'm really happy about the idea that that'll be useful and interesting because it's a subject that's very dear to my heart. The problem is I just want to ask all kinds of unreasonable computational questions, like why can't we just do everything in 3D with rotation all the time, and or things that we just don't know yet, like how do we with high fidelity bring that down to a 1D approximation? Like what is the way to parameterize that, or what are we trying different things right now, or do we have a couple of ways that is done and that's just how we're doing it? I don't know where that's at, but yeah.
Okay. Yeah, I think my takeaway is, actually I was really interested, Jane, in everything you were saying on your overshoot model. I recognize a lot of what you're saying from my simulations. We also get G-mode excitations, and yeah, there's a lot to explore there. And I mean, you say you're not going to learn anything profound by having a physically motivated model. I would actually say that's not true for white dwarfs. I think there is a good chance that we can have some profound results there because it allows us to extrapolate, hopefully, to cool white dwarfs. So there's some exciting things there for my research. And yeah, I didn't really discuss it before, but on the observational data side of things, there are actually a lot of constraints that we'll be able to place on additional mixing processes in the surface layers of white dwarfs, both through multi-object spectroscopic surveys and X-rays. So yeah, I just wanted to throw that out there, but feel free to ask me if you're interested. But yeah, otherwise, it's nice to meet everyone on the panel, and thanks to the organizers for putting this together.
All right, and let's thank our panelists.